All right, we broke up our waves unit into two separate subunits in which we talked about characteristics of waves, which are really just basics about waves. What is a wave? What does it look like? What are the parts of waves? And our second unit was wave behaviors, like how do waves act or react in certain situations. So we're going to begin by talking about basics of waves or characteristics of waves. So what is a wave? Well, a wave is just a disturbance that transfers energy through the matter. Now, the key here is that the waves transfer the energy. Energy is the only thing that's being transferred through the medium. Okay, now, medium is referring to the substance or the stuff that the wave is traveling through. And it could be a solid, liquid, or gas, or in some particular waves, it could be a vacuum. Okay, but in any case, the waves transfer the energy here. Now, there are two types of waves. There are mechanical waves, which we'll talk about a little bit, and electromagnetic waves. And they both have some similarities and they have some differences. For example, mechanical waves need a medium. This is a key characteristic of a mechanical wave. They need a medium. They need a substance to travel through. They need a solid, a liquid, or a gas to travel through. If they cannot travel through that solid, liquid, or gas, they cannot transfer their energy. Electromagnetic waves, on the other hand, do not need a medium, which means they can travel through solids, liquids, and a gas, as well as a vacuum. So these waves can travel through outer space. So the sunlight that we see from the outer space and the waves that that reach the Earth from the sun are all classified as electromagnetic waves because they do not need a medium. They can travel in a vacuum. Now, as far as the speed goes, mechanical waves increase speed in denser matter. So sound, for example, is a mechanical wave, and it transfers its energy through a series of vibrations in that medium. As those particles in the medium get closer and closer together, for example, as the medium goes from a gas to a liquid to a solid, the molecules in that medium get closer together. And as they get closer together, they can transfer their energy much faster that way. Electromagnetic waves actually do the opposite. Where mechanical waves increase speed in denser medium, electromagnetic waves decrease speed in denser medium. So it kind of has the opposite effect. So as that medium gets more dense, as we go from a vacuum to a gas to a liquid to a solid, the particles get closer and closer together. And as they get closer and closer together, it makes it harder for that electromagnetic wave, the particle, to travel through that medium because the molecules are in their way. So the more molecules that get in the way, the slower that particle can travel, the slower that wave can travel through. Mechanical waves are affected by higher temperatures, and they will actually increase their speed as the temperature goes up. And they do so by the way that the molecules react when the temperature increases. Now, you might think, well, if mechanical waves speed up in denser medium, and I know that cold air and cold water is more dense, well, it should travel faster in colder temperatures. However, that's not the case. The reason being, when those molecules are cooled down, they become more lethargic. They have less energy, they're moving very slowly. So as those particles move very slowly, they cannot transfer their energy as quickly as a warmer medium where the molecules are very excited, they're moving around very rapidly, very fast. They could transfer that energy a lot quicker as the temperature goes up. Electromagnetic waves, there's really no significant effect by temperature, so we're not even concerned about that. Mechanical waves can be longitudinal, which we'll talk about here in a second, or transverse. They could be one of two waves. Longitudinal, just for a quick reference, is like a compressional wave, A transverse wave is kind of like our snake-looking waves. Electromagnetic waves are only transverse waves. Okay, whereas electromagnetic waves can be either. Electromagnetic waves are only and all transverse. As far as speed goes, mechanical waves are slower than electromagnetic waves. Significantly slower, and that sound travels at 343 meters per second in air. Electromagnetic waves travel 3 times 10 to the 8th meters per second in space. So 300 million meters per second compared to a mere 343 meters per second for sound. So let's look at the first shape of a wave. The first shape is what we call a transverse wave. And transverse waves are the snake-looking waves that look like this. Okay? Now these are unique in that the medium, the particles in the medium, the substance that the wave is traveling through, moves perpendicular to the direction the wave travels. Now, the animation is not working on this slide, but if I was to watch this dot, the dot would move up and down. Every single one of these dots would simply just move up and down. While the energy, if I was to follow each one of these waves that are appearing here, the energy would appear to move to the right. So as the energy moves to the right, the particles are moving up and down, making this perpendicular to each other. So the medium, the matter, the particles in the substance travel up and down in relation to the energy, perpendicular to that. So an example of this would be light. Light is a transverse wave. If you've ever done the wave at a football game or a basketball game, when the wave comes to you in your section, your role is to just simply stand up and sit down. You are the matter, you are the medium, and the medium's moving up, but the wave is moving either left to right, perpendicular to your direction. Okay, so here is a drawing of a transverse wave, and we can see these areas that are high and then areas that are low, and then it goes up again and then it comes back down. And it creates that snake-like effect, up and down like a snake. Now, we can label these points and refer to these points as either a crest or a trough. The crest measures the highest points in my wave. So at this point, I have the highest point of a wave. We've got the highest point here. So these points are called crests. Troughs are the lowest points. I've got a low point here and a low point here. These are called troughs. Amplitude is a measure of the height of the wave. And the height of the wave is measured from our baseline, or as I like to call it, our equilibrium line. So this line right here is my equilibrium line. And I measure the height of the wave from that equilibrium line. And I'll measure from either the equilibrium line to a crest, or I can measure from the equilibrium line to a trough. Either way, those two measurements will be the same. So the amplitude can be measured here, the amplitude can be measured here. These two values will be identical because this equilibrium line, this baseline, transects our wave evenly. So I have equal parts above and equal parts below. The wavelength is the distance to identical points on the next wave. So if I want to refer to my wave at, let's say this point right here. This is my starting point, right as my wave is going up to this crest. The same point that marks the end of this one wave is all the way over here, where this wave is now going up, approaching a crest. So from this point over here to this point right here, this marks one wavelength. I can also measure that wavelength from a crest to the next identical point on the next wave, which is the next crest, this measures one wavelength. If I find a trough and measure to the same point on the next wave, which is the next trough, that is one wavelength. Okay, wavelength is a measure of distance in a wave. So here's an example of an electromagnetic wave. So electromagnetic waves are all transverse. So electromagnetic waves are unique in that they could travel through anything, solids, liquids, gases, and a vacuum. And all these waves travel at the same speed. They all travel at 3 times 10 to the 8th meters per second. Whether it be a radio, microwave, infrared, visible, UV, X-ray, or gamma, they all travel at 3 times 10 to the 8th meter per second. And I know they're transverse waves because they have that snake-like effect. Now, something happens as we go from the left side of the spectrum where radio is and move along to the right where gamma is. There are two things that are changing. Here is a measurement or showing me the wave's wavelength. So the length of each wave within radio, microwave, infrared, and so forth. Down here, I see a measurement of frequency, which is measured in hertz. What you notice is that as these waves go from the left to the right, the wavelength gets smaller and smaller and smaller. So it starts at 10 to the third, then 10 to the -2, then -5, -6, -8, all the way to -12. And you look that these long stretched out waves start getting closer and closer and closer and closer, showing me that my wavelength decreases. So the wavelength decreases as I move to the right. Now, another thing that's happening here has to do with my frequency. And I notice that my frequency of a radio wave is 10 to the 4th, which might seem like a very large number, but as I move to the right, I have 10 to the 8th, and 10 to the 12th, 10 to the 15th, all the way to 10 to the 20th. So what's happening is that as I go from radio to microwave all the way to gamma rays, the frequency, which is the number of cycles per second, increases. So this shows us that wavelength and frequency have an inverse relationship. So as the wavelength decreases to the right, my frequency increases, which allows these waves to all travel at the same speed. Now, one last thing that's occurring here is that as these waves move to the right, with an increase in frequency comes an increase in energy. So radio waves out here on the far left have a low frequency, which means their energy is very little, very minimal. Okay, these radio waves aren't really going to affect us or harm us in any way. But as we move to the right, these waves, with an increase in frequency, they gain energy. So visible lights, UV lights, X-rays, gamma rays, all of these waves can now have the potential to harm us because they have so much energy. They can damage cells. They can give you sunburn. They can cause abnormalities or deformations. They can cause changes to DNA. They can alter and destroy your cells in your body as we move to the right with an increase in frequency. A second type of wave shape that we're looking at is what we call a longitudinal, which is also called a compressional wave. And again, the animation is not working on this, but you can see in these waves, you can see like these little striations where it looks like there are bands. These are areas that have all the matter in that medium very compressed. And you have areas in between all of those that are decompressed, not so packed together. Now, what's unique about these types of waves is that the matter, the particles in the medium, move parallel to the direction the wave travels. So, for example, if my wave is traveling to the right, the energy is traveling to the right, then my particles are also moving in a similar fashion. And these two directions are said to be parallel. So a compressional wave or longitudinal wave, unlike a transverse wave that moves perpendicular to the medium, it moves parallel to the medium. And an example of this would be sound waves. Sound waves are compressional, longitudinal waves. And if you can imagine this red bar being a speaker, if this speaker is fluctuating back and forth, it's pushing up against the air molecules around it. And it'll compress those air molecules. And it sets off a chain reaction of vibrations throughout that medium, that air, until it reaches your ear. Okay, so here's a schematic of drawing an example of a longitudinal wave. Now, it's a little different than a transverse wave, but it's also similar. Okay, if you look down here, this looks or appears to be a slinky or a spring. And as this person moves the slinky, the medium, back and forth, the energy is traveling to the right. These two directions are considered to be parallel, meaning they will never intersect each other. Now, what you should notice right off the bat are these areas where the waves, the slinky or the spring, appear to be really close together. These areas are exactly what they look like. They are compressed together. They are compressions. These compressions are very dense regions. The areas in between where they don't seem so compressed together are less dense. These are called rarefactions. So I've got compressions being the highly compressed areas and rarefactions being the spaces in between these. Now, unlike a transverse wave, where I can measure the height of the wave as the amplitude, amplitude is measured as the density in a longitudinal wave. So as these compressions become more dense, they carry with them more energy, meaning their amplitude has increased. And I can measure wavelength the same way. If I can find the beginning of one part of a wave, let's say I want to find the beginning of this compression right here. I'm going to find the same point, the identical point on the next wave. So if I'm beginning at one compression, I want to begin at the next compression, which is about here. So from here to here, it measures one wavelength. If I measure from the beginning of this compression to the beginning of the next compression, this is also another wavelength. I don't have to measure from the compressions. I can measure from the beginning or the middle of a rarefaction and measure to the middle of the next rarefaction. Okay, this is still one wavelength, as long as you're finding or measuring the distance to the same point on the next wave. So with the waves, we can calculate things like frequency and period. And we've talked about frequency and period when we discussed circular motion. Frequency, which is abbreviated or symbolized with a lowercase f, is the number of waves over seconds. So it's the number of waves per second. Waves are also referred to as cycles. So a cycle is a wave. So it's the number of cycles per second. So one way you can calculate frequency is taking the number of cycles, dividing it by time, and you have your frequency. And frequency is measured in hertz, symbolized Hz. Period is the inverse of frequency. So instead of measuring the time, the cycles, the number of waves per unit time, period is measuring the time it takes for a single wave to travel. So period, which is symbolized with a capital T, is the time it takes for a wave to pass. So it's the time over the number of waves. And since period is measuring the time for one wave to pass, the unit for period is the second. Okay, this down here explains that frequency and period are inversely related. And you can see that they're inversely related because frequency is a measure of waves over time. Period is time over waves. They are opposites of each other also known as inversely related. So if I know the frequency, I can find the period. If I know the period, I can find the frequency. One other way to write this that I like to express to my kids is that frequency is equal to the inverse of the period, and period is equal to the inverse of the frequency. They're inversely related or oppositely related. Okay, now 2 ways we can calculate the speed of waves is by using our equation velocity equals, and this doesn't look like it transferred very well, but this is wavelength. Okay, so it should say velocity equals frequency times wavelength. And over here on the right, I've got velocity equals distance divided by time. This has not changed. We've had this equation in our pocket since day one. Distance or displacement divided by time. Frequency times wavelength gives me velocity. So when you're solving these, you just got to identify what information is given to you. If you know velocity and wavelength, you can solve for v. If you don't, but you have distance and time, you can solve for v that way. So this shows us that velocity is directly related to frequency. It's also directly related to wavelength. So if the frequency goes down, my velocity goes down. If the wavelength goes up, velocity goes up. Okay, assuming that the frequency or the wavelength may alter. Frequency and wavelength are inversely related. So if I'm maintaining a constant velocity, if my frequency goes up, then that means that wavelength has to go down. Which is why when we looked at our electromagnetic spectrum, as we moved from the left all the way to the right, our wavelength decreased, allowing for an increase in frequency, maintaining a constant 3e8 meters per second for those electromagnetic waves. All right, so we're going to continue on here, continuing to talk about waves, but more specifically, how waves behave or interact with certain medias. So our first wave behavior is known as refraction, and refraction is simply the bending of light. Now, light bends when it changes velocity, and it changes velocity when it enters different mediums. Now, we talked before when we talked about electromagnetic waves, and they were different from mechanical waves when they entered mediums of different density. And what electromagnetic waves do is, as they go from a vacuum to a gas to a liquid to a solid, they actually slow down. And when that velocity changes, when there's a decrease or even an increase depending on the density of the medium, it bends. And we call that behavior refraction. So we can see examples of that here to the right. If I placed a glass of water or oil, which we saw in class, and I placed a pencil or a straw or any kind of straight cylindrical object inside that cup or container, it would appear as if that object was cut in half and there were 2 different objects, but the reality is it was the same object. It just appears as if there are 2 because air, it has a density that is less than water or oil, and when light travels from air into water, it slows down, or even into oil, it slows down, and when it slows down, it bends. When it changes its density, it bends, also known as refraction. So it appears as if there are 2 separate objects. The reality is there is only one. If you've ever looked into a fish tank or an aquarium, if you look from the top down, you can see fish or objects or any other things that are in that aquarium. They appear in one location, but when you look from the side, they appear to be in a totally different location because the light is refracting, it's bending as it travels into different mediums. Our second behavior is one that's pretty common that we are probably more familiar with, and it's reflection. And reflection occurs when lights hit a medium or a surface, a substance, and it bounces off. So the key here is that the light is bouncing off of that medium. So a lot of times we'll see the reflection in a mirror. So we're seeing the reflection of light. We're seeing light bounce off of that mirror. You'll see reflection in glass, on windows. You'll see it in on car roofs or car hoods. It's bouncing off of that substance. Sound also has a similar behavior where the sound waves travel and they'll bounce off of a substance or a material. However, we specifically call that or refer to that as an echo, but it's the same premise, same behavior. Now, the law of reflection says that the angle at which the light enters a substance is equal to the angle at which the light bounces off of that same substance. Now, we discussed this when we talked about refraction in the lab, in that if you have a substance, let's say this is a mirror, or let's say it's a glass, I have a ray of light that is coming in. It's incoming, and we call that the incident ray. So the ray that is coming into the medium is called an incoming ray, or incident ray, excuse me. And that ray is going to bounce off of that substance and leave that material. Now, this bouncing off behavior is known as reflection. So we call this the reflected ray. The ray that is coming into the substance is the incident ray. And the normal, which is an imaginary line, is just there as a reference. The normal is always perpendicular to the surface. So if this is my surface going vertically, my normal is coming out here to the left, and it's 90 degrees from this surface. Now, this incident ray and this reflected ray are always compared to the normal. They are never compared to the surface. They're always compared to the normal. So you'll notice there's no angle measured here, and there's no angle measured here. They're measured within here, between the ray and the normal. Between the ray and the normal, that's where our angles can be found. So if we've got an incident ray, an incoming ray, then the angle that is formed here compared to the normal is known as the angle of incidence. And my reflected ray is forming an angle also compared to the normal, and this is called the angle of reflection. So we see it abbreviated theta I for angle of incidence, theta R for angle of reflection. And what is true is that no matter what angle this is, the angle of incidence, the incoming angle, it will always be equal to the angle at which it reflects off that surface. It's always equal to my angle of reflection. So the law of reflection says that theta I is equal to theta R. So in other words, the angle of incidence is equal to the angle of reflection. Again, theta, the angle, is always measured to the normal. Interference is one that we saw when we discussed standing waves and we saw the standing wave demo. Interference is when two waves combine to form a new wave. Now, when these two waves combine with each other, they behave in a way that we might think doesn't actually happen, but it does. When these two waves overlap each other, or when they collide with each other, they pass right through each other and continue in their original direction. Okay? So, for example, if I've got a wave that is a crest, and it's combining with another crest that is coming towards it. Let's say this crest has an amplitude of 5. This crest has an amplitude of 5. When those waves collide and overlap with each other, they're going to form a wave with a larger magnitude of 10. All I simply did was took 5 and added 5, and I got 10. Now, after they pass each other and they're done overlapping here, what you get is the crest that was originally on the right is now on the left, going to the left. The crest that was on the left is now moving to the right, or continuing to move on the right with the same magnitudes. Same is true if I had two troughs. So if I've got a trough of -5 and a trough of -3 moving towards each other, when they collide, they will form a trough of a larger magnitude, and I could determine the magnitude of this trough by simply adding -5 with a -3, and that gives me a trough with a magnitude of a -8. Now, once that once those two troughs have overlapped, the smaller trough is now on the left, continuing to move to the left, and the larger trough is on the right, continuing to move to the right. So they continue to move in their original directions. So when these two types of waves form in phase, we get what is called constructive interference, where the waves simply add together. Destructive interference occurs when two waves collide, but they kind of cancel each other out or to subtract or destroy each other, just like the name implies, destructive. So destructive means destroy. Constructive means you're going to build. And I'll show you an example here in a second. So destructive interference occurs, let's say I've got a trough of magnitude 2 and a crest of magnitude 2 and a trough of magnitude -3. When these two waves collide, they are out of phase because I've got a crest and a trough. No longer do I have two crests or two troughs, it's one of each. Now I'm going to figure out the resulting wave just simply by adding. I've got a +2 and a -3. 2 plus a -3 is a -1. The negative is going to indicate, it's going to tell me that it's going to be a trough with a magnitude -1. Now, once they are done overlapping, the trough is still on the left, moving to the left, and the crest is on the right, moving to the right. Now, total destructive interference can occur when when the waves actually cancel each other out in their entirety. So if I've got a crest of 2 moving to the right and a trough of -2 moving to the left, if I add a +2 with a -2, I get 0, which means for that split second, there's just going to be a flat line in my wave, where the waves are going to completely destroy each other, canceling each other in their entirety. But those waves will momentarily go away. The energy hasn't gone away. The energy is still there. The energy will reappear in the form of a trough moving to the left and a crest moving to the right. So this is known as destructive interference. Okay, and we saw those types of interference in a standing wave. We did the demonstration with the string where we created energy, or we added energy to that string by pumping a speaker up and down. When that speaker moved up and down, the energy transferred perpendicularly through the string. And when that energy reached the end, it reflected back on itself, and we got areas of constructive and destructive interference. Now, you can't see the animation, but what I'm going to do is I'm going to draw in the standing wave for you. So my wave is going to start right here, and you can see where the labels are. Okay, so I'm going to try to draw this wave as best as I possibly can to match those labels. So my wave is going to start right about over here. It's going to go up down, something like that. And once it gets to the end, it's going to reflect back on itself. So what you can see here, and I apologize for this drawing, is I could see what we call nodes and I could see what we call antinodes. So the nodes are pointing to the areas right here on this equilibrium line where my string normally is. And you'll see that there's not much amplitude. There's no amplitude at these nodes. So nodes have no amplitude. Nodes have no amplitude. In other words, they have no energy. Okay, these are areas of destructive interference. Now you'll notice that the other areas here within this standing wave have areas of high amplitude, and I can measure the amplitude and the antinode by measuring the crest and the trough. So these areas with high amplitude are known as antinodes. So the antinodes have a lot of amplitude. They have the most energy at these points. These are areas of constructive interference where their waves collide, forming a larger wave. So the most energy at the antinode, least energy at the nodes. Now I can look at this standing wave and I can count and determine how many waves I have in total by simply counting the antinodes. So if I've got an antinode here, crest and a trough, that's one wave. Got a crest and a trough here, my second antinode, that's two waves. A crest and a trough here, that's three waves. A crest and a trough here, that's four waves. So I'm counting 1, 2, 3, 4 antinodes, meaning there are 4 waves. And there will always be one more node than there are antinodes. So if I counted 4 antinodes, then that means there's 1, 2, 3, 4, 5 nodes. Resonance is a lab that we did with the tuning forks and the graduated cylinders filled with water. And all that resonance is simply the ability of an object to vibrate at a natural frequency. So if we create a vibration in the tuning fork, that tuning fork is going to vibrate at a certain frequency, and it's going to cause the air within that pipe, that column of air is going to resonate and vibrate at that same shared frequency. And we refer to that simply as resonance. Now, when we created our standing wave within the graduated cylinder, within the PVC pipe, what you ended up having is, let's say this is my pipe, and the water level was somewhere down here. What we had, I'll draw this in green. What we had was a standing wave that was formed. And you heard the loudest sound at the antinode. So the wave traveled and it reflected back. And it's at this point, this antinode here, that we heard the loudest sound. And we heard the loudest sound because we had the most energy. We were at the antinode. Well, the antinode occurred at 1/4 of a wave. And if we had a longer pipe, we could have heard the second antinode that would have occurred at 3/4 of a wave. If I would have raised this pipe up, the PVC pipe, too high, then that would have approached my node, my second node. And as I approached that node, the sound would have got quieter. And if I would have brought it back down, I'm approaching the first node, and the sound would have also diminished. And it was at this 1/4 of a wave at my antinode that I heard the loudest sound. Okay, diffraction is not one that we had a lot of demonstrations for. However, diffraction is when waves are forced through an opening or some kind of a slit or some kind of barrier. And you can see here in this diagram here on the left that all these waves are traveling in a straight path. All these waves are perfectly aligned, parallel to each other. And you've got a barrier here, and you've got a barrier here. Now all this energy is being forced to this tiny little opening. Now instead of all these waves continuing to move in that same parallel, orderly fashion, how they act or react is they bend and curve around that barrier. So you can see how these waves have curved through that barrier. Same thing is true here with this graphic. You'll see that down here at the bottom, these waves are perfectly parallel to each other. And you've got a barrier here and a barrier here. But once these waves are forced through this barrier, you'll notice that they no longer have that straight parallel fashion to them. They've got a curved manner. So this curvature, this bending around a barrier is what we call diffraction. The Doppler shift, the Doppler shift is typically witnessed when you see vehicles moving at a high rate of speed that are emitting loud sounds like sirens, like police cars, like ambulances, fire trucks. And the graphic isn't playing, but if this dot that's here at the center is moving in a certain direction, let's say a high rate of speed, that frequency, all those sound waves that are occurring in front of the object get very compressed. So if that object is traveling to the right, then all those sound waves in the front are very close together. And as that object moves to the right, all those sound waves that are kind of behind this object are more spaced out. And I know it's hard to see, and I apologize for this graphic, but the more spaced out they are, the lower that perceived frequency will be. The closer these lines are, the sound waves are together, the higher the frequency, which is why when you hear a fire truck come towards you at a high rate of speed, it sounds really loud up to the point where it passes you, and as soon as it passes you, that sound kind of drops off, almost as if the fire truck has turned down the volume as it passed you. But all that's happening is that these sound waves are becoming so stretched out and spaced out that the frequency seems to, or appears to be, a lot lower. Okay, shock waves, something we didn't really spend a lot of time talking about, and it's very similar when we're talking about Doppler shift, but this occurs when the speed of an object either equals or exceeds the speed of a wave as it travels through a certain medium. We've talked about planes or cars traveling faster than the speed of sound, and when that happens, so all the air that normally smoothly forces its way around the nose cone of the vehicle, whatever it may be, it can't get out of the way fast enough, and it creates that disturbance in the medium. And you can see here that these waves are created. There's a disturbance in the medium because the air molecules cannot get out of the way fast enough of this vehicle. And polarization. Polarization occurs when light traveling in certain areas blocked out due to the arrangement of medium. Now you'll commonly see polarization in sunglasses or window tint or window film. And how it works is, just for example, if I've got light that can travel either in this manner, maybe it's traveling in this manner, or maybe it's traveling at an angle like this. So light's traveling, and it's a transverse wave, but it's not always up and down. It could be left to right, it could be at a 45-degree angle, it could be at a 30-degree angle. It's at all different angles. So if I can create some kind of a material that can filter out that. So if I have a material that is arranged like this, then most of the light, or all light that is traveling in an up and down manner, will be able to pass through these little slits. But if I catch light that's traveling at an angle like this, it's probably not going to let that much light through. If I catch light that's traveling horizontally like this in a transverse wave, it's not going to let it through. It's only going to allow light traveling up and down vertically to pass through this film. Okay, if I want to increase that polarization, and on top of that I add a second layer, and the second layer has an arrangement that is horizontal. Well, now the light that was normally coming through here vertically as a transverse wave can't pass through. Light that's traveling horizontally cannot pass through either. So what you may get is a screen or a film that blocks out majority, if not all, light. Now, obviously that wouldn't be very effective for sunglasses because you would need to see out of them, but the engineers that design these type of sunglasses use some kind of arrangement that blocks out most light just by the arrangement of or the composition of that material. It blocks out most light and not all light because you still need to be able to see out of it.